In this problem, we study the Capacitated Facility Location Problem, which is a core decision in strategic supply chain design. The central question is where to open facilities such as warehouses or distribution centers, and how to assign customer demand to the open facilities. The total cost includes a fixed opening cost and a variable transportation cost, and the capacity limits are what make the problem operationally realistic. The scenario is strategic network design for a global retail company entering a new continent. The company has 15 candidate distribution center sites and must serve 100 metropolitan areas. Each site has an annual lease cost and a maximum throughput capacity, and shipping costs are known from every candidate site to every city. A poor choice can lock the firm into a high-cost network for years. This problem is strategically hard because the decisions are coupled and long-lived. Opening fewer facilities reduces fixed cost, but it can increase transportation cost, create long service distances, and push volumes toward capacity limits. The allocation decision must satisfy all demand while staying feasible for every open facility, which is why we need structured methods rather than ad hoc judgment. This problem uses 8 tiers, ranging from formal optimization to advanced computational and decision support methods. We start with a 2-stage stochastic programming model that handles uncertain demand. Then we use beam search and differential evolution as scalable heuristics. Transfer learning and digital twins add data-driven guidance and scenario testing. Finally, we consider human and artificial intelligence collaboration, fairness-aware modeling, and a quantum-inspired QUBO formulation. Tier 1 treats demand as uncertain rather than fixed. We represent demand using a set of discrete scenarios, each with a probability. In Stage 1, we decide which facilities to open before we know the realized scenario. In Stage 2, once a scenario unfolds, we ship from the open facilities to customers to meet that scenario's demand. The objective is to minimize opening cost plus expected transportation cost across scenarios. This slide defines the sets and indices used in the stochastic programming formulation. We have a set of candidate facility locations, a set of customers, and a set of demand scenarios. These indices organize the model so that we can express the same operational rules for every customer and for every demand scenario in a compact, rigorous way. These parameters capture the economic and operational inputs to the model. Each candidate facility has a fixed opening cost and a capacity limit. Each lane from a facility to a customer has a per-unit transportation cost. Demand is scenario-based, meaning each customer can have different demand levels depending on the scenario, and each scenario has a probability that sums to 1 across all scenarios. The decision variables represent what we control and what we adapt. The facility opening decision is binary. For each candidate site, we either open it or we do not. The shipment quantities are continuous non-negative values, and they are scenario-dependent, because in each scenario we may need to ship different quantities to satisfy the realized demand. The objective function adds 2 cost components. First, we pay the fixed opening cost for every facility we decide to open. Second, we pay transportation costs, but in a scenario-weighted way. That is, we compute transportation cost in each scenario, then take the expected value using the scenario probabilities. This creates a plan that is cost-effective on average under uncertainty. The demand satisfaction constraint ensures service feasibility. For each customer and for each scenario, the total inbound shipments from all facilities must exactly match the demand in that scenario. This prevents the model from leaving demand unmet or oversupplying customers when we compute the scenario-specific allocation. The capacity and linking constraint is the key operational constraint in the capacitated facility location problem. For each facility and each scenario, the total outbound shipments to all customers cannot exceed the facility capacity. At the same time, shipments are multiplied by the facility opening decision, which forces shipments to be 0 unless the facility is opened. This is what links the Stage 2 flows to the Stage 1 opening decision. This slide defines the facility opening decision as a binary choice. Operationally, this captures the yes or no nature of leasing or building a distribution center. Because this is a discrete decision, it drives the combinatorial difficulty of the problem, and is a core reason why exact methods can become slow at larger scales. Non-negativity enforces physical realism for shipment flows. We cannot ship negative quantities. This constraint also helps keep the allocation interpretable. Every shipment variable represents a real amount of product moved from a facility to a customer under a specific scenario. This diagram summarizes the two-stage structure. The facility opening decisions happen first, before uncertainty is resolved. Then, after the scenario is revealed, the model chooses the shipments as a recourse action to satisfy that scenario's demand. This separation is crucial. We are not allowed to change which facilities are open after demand is realized, only the allocation decisions. Beam search is a practical heuristic when the exact optimization becomes too slow. It explores the facility opening decision tree, but instead of keeping every partial solution, it keeps only a limited number of promising candidates at each level. This makes the search tractable while still allowing the algorithm to consider multiple alternative opening patterns. The key tuning parameter in beam search is the beam width, which controls how many partial solutions survive each level. At each depth, corresponding to whether we open each candidate facility, we branch into two choices: open or not open. We evaluate each partial solution using an estimated cost, typically the fixed cost plus a greedy assignment estimate under capacity. Then we keep only the best beam width solutions and prune the rest. This figure illustrates pruning in beam search. Instead of expanding the full search tree, which grows exponentially with the number of candidate facilities, beam search keeps only the top candidates at each level. The result is a controlled exploration that balances solution quality against computational effort. In this part, we move from the idea to the mechanics of the implementation. Key functions in this chunk include evaluate solution and beam search CFLP. As you read it, track what is computed, what is stored, and what gets updated each iteration. Also check stopping rules and guardrails so iterative logic stays stable and does not drift. A practical check is to run this section on a tiny test case and confirm intermediate values before scaling up. In this part, the code makes the slide method executable. As you read it, focus on the sequence of steps and which variables are carried forward, because that is where most implementation bugs hide. A practical check is to print or log a few intermediate quantities so you can verify that the update logic behaves as expected. Differential evolution is a population-based meta-heuristic. For the capacitated facility location problem, we adapt it by using a real-valued vector as an encoding. Each position represents the priority of opening a facility. We decode the vector into a discrete opening decision by thresholding or selecting the top candidates, and then assign customers using a greedy heuristic that respects capacity. This slide highlights the mutation rule used in differential evolution. A new candidate vector is created by combining 3 other population members and scaling the difference between 2 of them. Even though the original method is continuous, the resulting vector can be interpreted as opening priorities that are later converted into discrete facility choices. This figure illustrates how differential evolution creates new candidates. The key idea is to generate variation by differences between existing solutions, rather than by random perturbation alone. Over many generations, selection keeps the candidates that lead to lower total cost after decoding and greedy assignment. Transfer learning helps when a company enters a new market with limited local data. We train a model on a mature source market to learn what location features correlate with successful facility performance, such as demand density, proximity to transport hubs, and land cost. Then we fine-tune the model on the target market so the learned representation adapts to local conditions. The output is a suitability score that can guide facility selection. This diagram shows the transfer learning pipeline. A model is first trained in a data-rich environment, where many examples are available. Then it is adapted to a data-scarce environment by fine-tuning a subset of layers. The goal is to avoid starting from scratch and to reduce the cold start problem for strategic network design. A digital twin extends facility location beyond a static optimization. It simulates facilities, transportation networks, demand behavior, and inventory dynamics. With this environment, planners can run disruption scenarios, fuel price shocks, and demand surges, and observe cost, service, and resilience outcomes. This turns network design into a risk-aware planning exercise. This figure shows a system of systems architecture for a digital twin. The idea is to connect facility operations, transportation, customer demand, and inventory behavior in a unified simulation. This helps validate whether an optimized facility plan remains robust when real-world variability and disruptions occur. The Centaur model combines computational search with human judgment. Artificial intelligence can propose multiple strong network designs quickly, but humans can recognize unmodeled risks such as political instability, floodplains, or long-term strategic considerations. The human then adds constraints or excludes sites, and the system re-optimizes, creating a loop that blends speed with context-aware reasoning. This figure visualizes the iterative partnership between a human planner and an optimization system. The planner evaluates and guides, and the algorithm recomputes. Explainable outputs are important here because the system must justify why it recommends a certain facility pattern, so humans can trust and refine the decision. A purely cost-driven solution can create inequitable outcomes. A value-aligned approach adds fairness metrics, such as limiting the worst-case travel time for underserved areas, or ensuring similar delivery times across socioeconomic groups. This transforms the problem into a multi-objective decision, where efficiency and equity must be balanced rather than optimized in isolation. This figure shows a Pareto front. Each point represents a network design. Moving along the curve typically improves one objective, such as equity, while worsening another objective, such as cost. This helps stakeholders visualize the trade-off and select a solution aligned with organizational values. For very large instances, the problem can be computationally challenging. Quantum annealing approaches require converting the model into a quadratic, unconstrained, binary optimization form. Because the formulation is unconstrained, the original constraints must be embedded as penalty terms. The hope is that exploring the resulting energy landscape can find high-quality solutions for difficult combinatorial problems. This slide shows the general energy form used in quadratic, unconstrained, binary optimization. Binary variables represent decisions, and the objective is a quadratic function of those variables. The matrix defines how individual decisions and pairwise interactions contribute to the energy, which the annealer attempts to minimize. This slide shows a penalty term that enforces a constraint. For example, if each customer must be assigned to exactly one facility, we add a squared penalty that becomes 0 only when the assignment rule is satisfied. Choosing a sufficiently large penalty coefficient makes infeasible solutions unattractive in the energy landscape. This figure illustrates the idea of an energy landscape. Each configuration of binary decisions corresponds to an energy value. The goal is to find the lowest point. In practice, the quality of solutions depends on how well the original objective and constraints are encoded into the quadratic form. These practice questions help you apply the tiered toolkit. You are asked to write a complete two-stage objective for a small stochastic example, reason through how beam search expands and prunes solutions, and decode a differential evolution priority vector. You also describe what data is needed for transfer learning and digital twin testing, and you write a quadratic penalty term for a quantum-inspired assignment constraint. The Capacitated Facility Location Problem combines long-term investment decisions with operational feasibility. Stochastic programming provides a robust baseline under uncertain demand. Scalable heuristics and meta-heuristics explore the combinatorial opening decisions. Data-driven methods, simulation, and human-centered decision support expand the toolkit, and fairness and quantum formulations show how the problem connects to broader strategic and societal considerations.